Hello and welcome to our lesson on arithmetic sequences and series. So we've talked for a couple of topics now about what a sequence is and that a series is just the sum of the terms in that sequence. Today will be a focus on sequences and series that are arithmetic. So what does it mean for a sequence to be arithmetic? Well, again, a sequence is just a list of numbers, technically a list of outputs that are produced by a function that we call a sub n, and those inputs to that function are the natural numbers, and when we input those natural numbers we get this ordered list, which is our sequence. Now if a sequence is arithmetic, again that's going to be the focus for this topic, it means there's a distinct type of pattern. So this is an example here of an arithmetic sequence, and I'm guessing you can see the pattern. So if I want to go from 2 to 6, and then 6 to 10, and then 10 to 14, the pattern is I am adding a 4 every time. So we would say that the difference between each of these terms is 4. And so I can continue this list. 14 plus 4 would make 18, and 18 plus 4 would make 22, and this would just continue on forever. So when a sequence has that type of pattern, when I say that type, I mean there is a common difference between each of the terms. So you're either adding some fixed amount or you are subtracting some fixed amount to get a common difference. We have an arithmetic sequence. So if it's arithmetic, again, there is a common difference between consecutive terms, which means you can either add the same number to get from one term to the next, or you can subtract the same number to get from one number to the next. Now we define that common difference using the letter D. In this case, we would say that the common difference is 4. Now when we're getting that common difference of 4, moving from the first term forward, we say we're adding that 4, but the common difference we find by taking a term and subtracting the one before it. So we define D as a sub n plus 1 minus a sub n. Now generally we would take a sub n a term and subtract the previous term using this notation, but the smallest input is 1, and if I input a 1 here, we end up with a sub 0, and that's not defined. So we start with a sub n plus 1 and subtract the previous, which would have to be a sub n. So for instance, if I was looking at a sub 2, then a sub n would be 1 less than that, so a sub 1. That would be the smallest difference we can find. So that common difference we find by taking a term and subtracting the one before. So the 4 that we see here we can find by taking 6 and subtracting 2, or taking 10 and subtracting 6, and so on. But since we're adding 4, that common difference is a positive 4, whereas here I can see to get from 3 to negative 2, or negative 2 to 7, or negative 12 to 5, that I would be subtracting 5. So we would say that the common difference is a negative 5. And again, you could find that also working backwards. Take a term and subtract the one before it. Negative 2 minus 3 would take us to that same negative 5. So if I wanted to find a few of the missing terms here, negative 12 minus 5 would be negative 17, and negative 17 minus 5 would be negative 22. And then if I had to find a term going the other direction, instead of subtract 5, I would add 5. So 3 plus 5 means that first term has to be an 8. Okay? So if it's an arithmetic sequence, again, it's just a list that's generated by adding or subtracting some constant to get from one term to the next, and we call that constant that we add or subtract the common difference between the terms. We call it D. Okay? Now I want to connect this to something that we already know. Arithmetic sequences are linear in nature. So let's suppose our arithmetic sequence is the numbers 5, 7, 9, 11, 13, and so on. When I say that list is 5, 7, 9, 11, and 13, I mean those are the outputs for a function. So if I was to put them in a table, the 5, 7, 9, 11, and 13 would be a set of outputs. They would be what we call a sub n, right? That's what we call our functions, not f of x or something of that nature. Now the inputs we know are the naturals. So if I input for n 1, the result is 5. Input a 2, the result is 7. Input a 3, the result is 9. Input a 4, the result is 11. And input a 5, the result is 13. And we could keep making that table. But again, what I want to show you is if we were to plot these points where we connect the inputs and the outputs of this sequence, you're going to see that an arithmetic sequence is linear. So at 1, 5, we have a point. At 2, 7, we have a point. At 3, 9. At 4, 11. and at 5 and 13. And I could, again, keep going. N can keep getting larger, but we can't go the other direction. Remember, the smallest input, smallest natural number is 1. But you can see, if this was a normal continuous linear function, we would go ahead and connect these with that line. This is going to be a discrete function, but it's still linear. There's a constant rate of change between these points. So if I asked you to write an equation for a line, whether it's a continuous line or a discrete connection of linear points, we're basically doing the same thing. So pretend for a second I asked you to find the equation for this line here. Well, you would be writing a y equals mx plus b type of equation, and you would say that y would equal, well, the slope between these points is a rise of 2 and a run of 1, so our slope is 2. And then b, where it crosses the y-axis, happens to be 3. So that y equals 2x plus 3 equation, again, that applies to that continuous line, but it's the same formula that we could use to produce the points that are on our graph. We just wouldn't connect them. So let me get rid of all this. Y equals 2x plus 3. Let's hang on to that for a second. Oops, went too far. Is not only going to represent that continuous linear function. If I wrote it with our notation here, we would say a sub n equals 2n plus 3. That happens to be the explicit formula that produces this sequence. So we have, again, if I input a 1, 2 times 1 would be 2, plus 3 makes 5. That's exactly what I see here. Input a 2, 2 times 2 is 4, plus 3 makes 7. That's what I see here. So the same inputs and outputs, so the same function. Okay, we just have to be able to get that whether we are looking at a continuous line or this discrete list of points. So we need to be able to write this explicit function. Now, we just saw it come from y equals mx plus b, but we use different notation here, so let's try to make the connections, all right? When we are writing a y equals mx plus b equation, which is what we're doing here to write an explicit formula, we don't use y. We use a sub n, and m, that rate of change between the points, let me do this in different color, that rate of change, that rise and run, that m of 2, that is precisely the common difference between our 2 points, right? Our common difference, what we're adding to get from one number to the next, is 2. So instead of calling this m, we're going to call this our common difference. And here, we don't use inputs called x, we call our inputs n, so I'll put n in. And then the really interesting part here is b. So b is where a continuous linear function would cross the y-axis. A discrete function for an arithmetic or any sequence isn't going to touch the y-axis because the smallest input is our natural number 1. Now we can't cross the y-axis, but we can still figure out what that value would be if we were going to cross the y-axis, right? So if I was going to cross at this point here, how do I get it? Well, I take my first term, so a sub 1, which was at 5, and I subtract that common difference, and I end up at this value. So if I take a sub 1, which was 5, subtract my common difference of 2, I land at 3. So I'm going to generalize b by saying it will be our first term minus our common difference. And now, instead of a y equals mx plus b formula that we can use to write linear equations that are continuous, we have the same formula but in terms of our sequence notation. Now, when we actually use this formula, it's cleaned up a smidge. So let me show you the cleaned up version. I have a sub n equal to, these two terms have a d in common, so I'm going to put them together. So let me move a sub 1 here, and then rewrite the dn minus d here. Because they have a d in common, we can factor that out. So we're going to say a sub 1 plus d times n minus 1 is our formula to write the explicit rule for any arithmetic sequence. So just like this, y equals mx plus b, we could use to write a linear function that is continuous. This we can use to write the explicit formula, which is our function for an arithmetic sequence. Okay? I hope that makes sense. So remember, when we're calculating this explicit formula, it's so that we have a formula we can use to find any term that is on our list. So for arithmetic sequences, our explicit formula is always of that form. We can say any term on that list will be our first term plus our common difference multiplied by n minus 1. Anytime I want to find an explicit formula, this is what I can use. So let me just go back to the example we saw up here. Okay, so we just generalized and said if I wanted to write an explicit formula, I know we have it, it's 2n plus 3, but if I wanted to write an explicit formula for this set of numbers, that explicit formula a sub n would be my first term of 5 plus my common difference of 2 multiplied by n minus 1. And so if we simplify that, you have 5 plus 2n minus 2. And when you combine the 5 and the minus 2, you get that y-intercept that we would have had if we could go there. And we end up at that 2n plus 3, which is exactly what we said for our linear function. Okay, so let's practice with a few more examples, just writing explicit formulas and using the explicit formula to find terms on a list. So for this third problem here, if I wanted to write the explicit formula for the sequence 3, 8, 13, 18, and 23, I'm going to say my explicit formula a sub n is always going to equal a sub 1, which I know is my first term, that's going to be 3, plus my common difference, and I can see that common difference between my terms. What I'm doing to get from one to the next is adding 5, so it'd be plus that common difference of 5 multiplied by n minus 1. So when I'm using this formula, again, I'm trying to write a formula just like when I write y equals mx plus b, x and y stay in the formula. I'm replacing m and b. When I use this formula, n is going to stay in our formula, and I'm replacing a sub 1 and d. Okay, those are the only two values I would plug in, just like in y equals mx plus b, I plug in my m and my b. So plug those two in, and this would be a perfectly acceptable way to leave the answer. But we could also simplify this. We could also say a sub n is equal to 3 plus 5n minus 5 when we distribute, and then because I have like terms there, I could say a sub n is equal to 5n minus 2. And this is the form I prefer, but any one of those forms is technically fine because it would generate that same list. Now, we use that explicit formula. You should be familiar with the formula. Hopefully you've seen this before at some point in your mathematical career. I actually don't like to use it though myself because I know this is linear. And so let me just show you how I would do this. If I was trying to write my explicit formula, I can get right to this without having to take these steps to get there. So I know that I'm trying to write a y equals mx plus b type of equation. I just know it's going to start with an a sub n. And I know m is going to be that common difference, so I'm going to have a 5n here. And then b is not my first term on the list, it's the one right before it. And so instead of adding 5, if I subtract 5 from 3, then 3 minus the 5 means negative 2 has to be that value connected. So my y equals mx plus b. Now I know my sequence is not getting there, but I can still use my common difference to write that rule, if that makes sense. So again, I can jump right to that answer without having to use the generic formula, which is useful, but again, if we can work smarter and not harder, then why not? So let's try this again. I'm going to, again, show you using the formula, and then I would show you what I would do. So if I wanted to find the 50th term of this sequence, I would probably write my explicit formula first, and then input a 50 to figure out what that 50th number is going to be. So I know a sub n is equal to, the first term here is going to be 12, plus my common difference, I am subtracting 4. So this needs to be a minus 4, and then we multiply by n minus 1. Now that's going to end up simplifying to a negative 4n, and then instead of subtracting 4 this way, I would add 4 this way, so I know it's going to be a plus 16. Now you can also see that here, negative 4n and then a plus 4. That plus 4 combines with 12 to make that 16. Okay, so if you simplify it or leave it in the formula, either way is fine. We have our explicit formula. The purpose now of writing the formula is to use it. So if I want to find the 50th term, that means n is 50. Let me plug it in, and I can plug it into either form. So I'm going to go ahead and plug into this one. A sub 50 is going to equal negative 4 times 50 plus 16. So negative 200 plus 16, which would be negative 184. So we would say a sub 50
is equal to negative 184. And I better just not. I mean, sometimes I lack confidence, I'm not gonna lie. No, I know how to add and subtract, but you just never know. Like, I don't know, my brain, it's not perfect. Okay, so there it is. We can write an explicit sequence. We can use it to find any term. That's the whole point of writing one. So this would be a good place for you to pause the video and try it out. If you don't want to, that's okay too. Let's go ahead and knock this out. So find a sub 100 of an arithmetic sequence. That means find the 100th number, given that the first number on the list is 10 and the common difference is 6. So a sub n, my explicit formula would be a sub 1, which is 10, plus my common difference of 6 multiplied by n minus 1. Or I could just jump to a sub n equal to 6n, because my slope, my common difference is 6, plus if my first number is 10, instead of adding 6 to get to the second number, if I subtracted 6 to get to the previous number, the continuous linear function would cross the y-axis at at 4. So subtract 6 and I get a plus 4 here, which is exactly what we'd see if we combined this negative 6 with this 10. Okay, so either one of those forms is perfectly fine for the explicit formula. Now we are trying here to find the 100th term, so let's plug in 100. And I'm going to go into this one, although either one would be fine. Actually, just for variety, let me go into this one. So a sub 100 equal to 10 plus 6 times 100 minus 1. So 600 minus 6 would be 594, plus 10 would be 704. Yeah, don't trust me. Plus 6 times 100 minus 1, and yay, I can still math. So we're going to say a sub 100 is 604. If we were to make this list starting at 10, adding 6 100 times, we would end up at 604 for that 100th term. Okay? Hopefully we're doing all right. Let's move along to the recursive definition. If we're defining any sequence recursively, we know that our formula is based on previous terms. Unlike the explicit formula where I can input any natural number and get the output, find any term on the list, the recursive formula means to find a term, I have to know what happened before. So the recursive formulas define terms with respect to previous terms. If I want to then recursively define an arithmetic sequence, it's pretty simple, because every term is just a common difference away from the previous term. So from my previous term, I'm either adding or subtracting. I'm always adding the common difference. If it's something we subtract, the common difference is going to be negative. So basically, to define an arithmetic sequence recursively, well, we have to state the first term. That's important. We have to know where the list starts, and then we need to know the common difference. So any term on our list will always be the previous term plus that common difference. And then we would always state here for n greater than 1, because that a sub 1 will be defined. Okay, so for example, if I want to define this recursively, not with an explicit formula, although I could do that, I would say a sub 1 is 17, and then a sub n, any other term, would be the previous term, a sub n minus 1, plus the common difference here. What I'm adding each time look like 6, so I will say plus 6, and that is for n bigger than 1, because 1 was defined already. And then the same thing here. I would say a sub 1 is equal to 5, and then any other term on this list would be the previous term minus 1. So we're subtracting 1 to get from one number to the next here. And again, this would be, and that looks so sloppy, hang on, minus 1. This would be for n greater than 1. Now again, a good opportunity for you to try this if you want to pause the video and give it a shot. But you should be able to look at an explicit formula for an arithmetic sequence and still define it recursively. So we need the same information. If I said to define this recursively, I need to know what the first number is. Well, I know how to find that. If I have a rule and I have to find it, just plug the 1 in, input 1 for n. So negative 3 times 1 would be negative 3, and negative 3 plus 1 would be negative 2. So I know this list would start at negative 2. And then any other term on this list is going to be the previous term plus my common difference, which is the slope here, right? It's the rate of change between my points. So I know I'm going to be subtracting 3 each time I move along this list. And that is, again, for n greater than 1. All right? So we could write explicit formulas, use them to find terms. We can write recursive formulas, again, use them to find terms if we needed to. And then the last thing, the last piece of the puzzle is we should be able to evaluate an arithmetic series, and that means we are finding the sum of the terms of an arithmetic sequence. So if we have all the terms or whatever information we have, we've got to be able to find the sum. So depending on the information, we have a couple different paths we can take. There's always the long path, right? If you're asked to find the sum of a list, you can just list all those numbers and add them up. But we want to avoid the long path if we can. So a couple other options aside from the long path. We can use our summation notation, and you can see that in problem number 7 here. This is summation notation already. I would probably still use summation notation here. But you're only going to be able to use the summation notation if, one, it's already in that notation, or if we know the number of terms, right? If I know, like this one, I'm going from the first to 18th term, and I know the explicit formula. Those are the two components I have to use or have to know for that notation to work. So I have to know the number of terms on the list, and I also need to know the explicit formula, or at least be able to find that explicit formula, okay? Now there's also, in addition to the summation notation, there's also an actual formula to calculate the sum that does not use the notation. So a formula says, for arithmetic sequence or a series, says that the sum for n terms on an arithmetic or in an arithmetic series will be n divided by 2, so that's the number of terms divided by 2, multiplied by a sub 1 plus a sub n. So again, to use this formula, I have to know the number of terms, because that's n. I also have to know the first term, because that's a sub 1. And then a sub n here, right? A sub n is going to match the n here. That's the, if n is the number of terms, right? So if we're finding the sum for 5 terms, a sub 5 would be what we're looking at in this spot, which would make it the last term. So whatever n is, it's going to make this the last term of the sequence. So if I want to use this formula, again, got to know the number of terms, have to know the first term, and have to know the last term. So the first term, obviously, a sub 1, and the last term ends up being our a sub n, okay? So we're going to look at a few situations, try to determine what's better, and if all else fails, we take the long path of listing out the numbers and adding them up. Okay? So first one, remember when we take our quiz for this module, we will not have a scientific calculator or a graphing calculator. So even though we have summation notation options in those calculators, we want to be able to just do this with a basic 4-function calculator. All right? So here, if I want to evaluate this sum, I would first separate this out. I would make this the sum, well, 4 times the sum from n equals 1 to 18 of n. And then I'm going to subtract the sum from n equals 1 to 18 of 6. So we had a formula we talked about in our previous topic for n here. This is going to end up being 4 times for n, or in our formula it's I, but it's just a variable. So the formula said to take the upper limit of our sum, which is 18, and then n plus 1, which would have been 19, or the upper limit plus 1, and then divide by 2. So that's just a formula we talked about in our previous topic. And then we're going to subtract from this the sum of 18 constants here, another property we talked about yesterday. We can evaluate this piece just by multiplying 18 by 6. And so into the calculator we go. And let me see, 4 times a fraction, 18 times 19 in the numerator, divide by 2 in the denominator, and then subtract from that 18 times 6, and we end up with 576 for our sum. So if I was to list out the 18 terms created by this, by inputting the 1, the 2, the 3, all the way up to 18, and then add them up, I would get to 576. Now, just so you can see, and we can verify work, it's helpful. If you go into functions and scroll down till you see sigma, you can just input this equation or this summation notation as is. So I can go from n equals 1 to 18 up here. Come on, calculator. And then here I can put in my 4n minus 6. I need to go to my keyboard to get n in there. And how about we fat fingers function here? There we go, we get the same thing. So if you want to use the summation notation to verify your work, that's totally fine. But remember, you're not going to get that when you take your quiz. So expanding it out using the properties and the rules we talked about in the previous topic would be helpful. Okay, so let's try another one. Actually, put my calculator away for a second. Okay, so here, different notation, a different setup for the problem, but we're going to do the same thing. So this says find the sum for 20 terms, and we know the explicit formula there. So this is written differently, but I can put this in summation notation, right? This says find the sum of 20 terms, so we're going to go from 1 to 20, and we know our explicit formula is negative 2n plus 5. So this is really just like the last one. I'm going to split this up to negative 2 times the sum from n equals 1 to 20 of n, and then I'm going to add the sum from n equals 1 to 20 of 5, our constant 5 there. So this will be negative 2 times, we have our upper limit, and then 1 more than our upper limit divided by 2. And then here we're just going to multiply that constant by 20, so the upper limit by the constant 20 times 5. And then into the calculator we get our sum. So let's see here. Negative 2, and then a fraction, 20 times 21 divided by 2. I don't know why I put both those 2's in there when I knew they would cancel, but let's just go with it. Plus 20 times 5, which again I know that's 100, but I'm just going to type it in. So I get negative 320. And now I'm just going to verify this with my sigma notation that I've already typed into the previous spot. So let's put 20 in there instead. And let's put negative 2n. Come on, calculator. Plus 5 and negative 320. So I verified my work. Okay? So there we go. We've evaluated 2 of our sums. Now sometimes different information is given, like in this one. I don't have an explicit formula, so if I don't have the explicit formula, it wouldn't be that hard to write it. We just practiced doing that. But I do have what is necessary for the other formula. So number of terms, first term, last term, all sitting on this list, right? This would be the first term. This would be the last term, a sub 12, and I know there are 12 terms. So I'm going to use the other formula for this case because it's set up perfectly for that one. So I would find the sum for these 12 terms. The formula says it's going to be n over 2, so 12 over 2, multiplied by a sub 1, which is 1, plus a sub n, which again n is 12. So a sub 12, last term on the list, is going to be 45. And that math wouldn't even be that hard, but again, just so I don't do anything silly, I'm going to go to the calculator and put in my 12 divided by 2. I feel silly just typing that in. And then, again, 1 plus 45, silliness, but it's fine. So 276 is the value for that sum. So even though we don't have the whole list there, if I wanted to expand that list, because I can see I'm just adding 4 to continue, I could write the whole thing out and add it all up, but work smarter, not harder. Alright, so here's the next one. It's a little bit different. In this one I know my first term, I know my last term, but I do not know my number of terms. And whether I want to use summation notation or my formula, I have to know the number of terms. So how do I go about finding the number of terms? This is where our explicit formula is really going to be helpful. The number of terms is n, and that explicit formula has a spot for n. So I'm going to start this by writing my explicit formula. So I would say a sub n is going to equal the first term, negative 50, And then my common difference, I can see I am adding 15 to get from one term to the next. So this will be plus 15 times n minus 1. Or the cleaned up version, my slope of 15 times n, plus if I subtracted 15 to go backwards, my like zero term that doesn't really exist on this list would be a negative 65. So there's my explicit formula in two different forms, whichever one you like. This is going to help me find n. I don't know what n is, but I know a sub n, my last term, is 400. So I can take this last term, a sub n, whatever n is, and plug it in here. So if I put 400 in and leave the equals 15n minus 65, now I have an equation I can use to figure out what n is supposed to be. And so I add the 65 over, so I get 465. Let me just separate this. Okay, add the 65 over. I'm skipping too many steps. Let me show some work. So I have 465 equal to 15n, and then divide by 15. So 15 goes into 46, what, 3 times? Would be 1 left over, plus the 5 is 15, so 31. Just let me use my little pacifier here. My crush, 31. There it is. So now I know there's 31 terms on this list. And now I have options. If I want to use my summation notation, I can. I have my explicit formula. I know how many terms I have, so I can rewrite it and evaluate that way. But now I feel like I'm in a situation more similar to number 9. I have my first term, I have my last term, I know my number of terms, and this formula is a little easier to handle than evaluating with the summation. So I'm going to go with my second formula, which says that the sum for these 31 terms is n, 31 divided by 2, and then a sub 1 plus a sub n. So first term, negative 50, plus the last term, which was 400. And then into the calculator we go. So 31 over 2 multiplied by negative 50 and 400, and we end up with 5,425. And I'm just going to go ahead and verify with my summation notation since I have my calculator handy. Why not, right? So we're going from terms 1 to 31, and the explicit formula was 15, I should have left n in there, n minus 65, and there it is, 5,425, so we're confirmed. Alright, so I have one last one. Again, a slightly different information given in a slightly different way. If you want to pause the video and give it a shot, cool. If not, let's knock this thing out. So, again, I need to know the number of terms, whichever way I want to do this, which I do. I know there's going to be 30 terms on this list. And then if I want to use my summation notation, I need an explicit formula, so I would have to find that to use that notation. If I want to use the other formula, I have to know the last term, and I don't have that one, and I would have to find the explicit formula to find that last term. So, to me, the easier path is to use the summation notation. It requires a little bit less work. I need the number of terms, I have it. In either case, I would have to find the explicit formula, but with summation notation, I would be done. With the other formula, after I find the explicit, I'd have to input 30 to figure out what the last term is. So you've got the option. You can do whatever makes you happy, and if that's neither one, you've got to pick one. I'm going to go with summation notation. But I need my explicit formula. I need a sub n, which is a sub 1 plus my common difference is 5 multiplied by n minus 1. Or I can say a sub n is equal to 5n, and then instead of adding 5, if I subtracted 5 from 3, I would get negative 2, which is exactly what I would get if I put the negative 5 with the positive 3. Okay, so either one of those I can use for my explicit formula. And now I'm going to put this in my summation notation. So I'm looking for the sum of 30 terms. So I can say I equals 1 to 30, or n, or j, or k, whatever variable you want, of, I don't know why I changed it to I in this one. Let me go back to n, because I have n over here. So I'm going to go n equals 1 to 30 of the sequence formed by this explicit function. Okay, so 5n minus 2, and now I can piece this out. So when I separate it, this is 5 times the sum from n equals 1 to 30 of n minus the sum from n equals 1 to 30 of 2. So this is going to be 5 times upper limit, 1 more than the upper limit, divide by 2, minus, we're going to multiply the upper limit and that constant, and then we go to the calculator to get our final answer. So here, 5 times a fraction, 30 times 31 divided by 2, and then let's subtract 30 times 2, and we're at 2,265 for our sum. And just because we can, let's verify if we're finding the sum for 30 terms. And we have a 5n minus 2. We better get the same thing, and we did. We're good. All right, so verified. All right, so a variety of examples, writing and using explicit formulas, writing and possibly using recursively defined formulas, and then an option of ways to evaluate a series, which is just the sum of the terms in our sequence created by one of those explicit or recursively defined formulas. All right, so it's a lot going on, but nothing overly difficult. As always, though, if you find yourself running into some trouble, needing some help, then just reach out. Until next time, take care.